Alright, this is for those who would like to benefit a little bit of review ahead of time. We are looking now at alkene reactions. Alkene reactions are or electrophilic addition reactions. As we talked earlier, alkenes tend to be more nucleophilic because they have these pairs of electrons available, so they will do this to any electrophile. Any electrophile, when it approaches, this is the first course of action, and when they do that, there is a transition state created where the E is now coating these two carbons with a reasonable equal behavior. The positive charge is now shared. This now has a choice of having these two choice, showing these two bifurcations is called regiochemistry. Regiochemistry is offer of two choices. If there is no choice, then there is no regiochemistry. Now that it has two choices, we can draw structures that each of these choices offer. When these electrons, the pi electrons from here, are permanently used to make a bond there, this carbon will have the positive charge, or when E starts living with this one, positive charge will be here. Now when these two choices are offered, the molecule has to make a decision now. Which route do I go? So if you look from an energy point of view, energy diagram point of view, the alkene and electrophile were here, and now they went through this route. So this is A, this is B. B is a transition state, right? Now B can result in a C1 or C2. Where is C1? C1 is somewhere here. Now compared to C1, wherever the C1 is, C2 is significantly below here. C2. Why C2 is below here? Because this is a tertiary carbocation, this is a primary carbocation. When there is a choice of going there, do I really have to climb that high? I can actually sneak in this way, right? I can even, according to the transition state theory, right? As long as the intermediate is here, transition state is here. If the intermediate here is, transition state has to be slightly higher. So the route that I'm having to take now doesn't have to go this way. It can even go this way. It's not that it has to climb all the way and come down. It can, the transition state for this intermediate doesn't have to be any higher than, slightly higher. It doesn't have to be that high. So what it means is the actual activation energy to be invested is far little compared to going through this one. So obviously that, crossing that, see, I'm crossing that out. Crossing that would be a sign of choice. A choice would be regio-selection. Regio-selection, regiochemistry is offering two choices, but making one of them out of the two is called regio-selection. So by doing this, we selected this one to go forward. We selected this molecule to go forward. Okay, that's the key. Now comes, there is a new offer. So right now we are here. We have to reach final location. We have to reach final location. Okay, that's different. Now let's see what is the next step. I'm going to draw this in a more what do you call, three-dimensional way. So this is a sp2, sorry. So I'm going to draw this. Let's say this is R1, this is R2. There are two H's here, right? And that's a E. So what does it look like? It's going to be a R1, R2, there is an empty p orbital with a vacant, and then what we have done now is this used to be what? sp2, this used to be sp2, this used to be sp2. These two carbons used to be sp2. Now suddenly this has turned into sp3. That means you can see my wedges and dashes changing the direction. They are going to go like this, right? Because they have to make a place for that E. E has been added there, right? So there is my second, those are two H's. So this is now sp3 carbon. But this is sp2. Okay, keep that in mind. The nucleophile, whoever is coming in now, has two choices. E is the first adding group, whoever that is. Let's not get bogged down by the E as the first group, whoever it is. The nucleophile has to approach this carbon. Now nucleophile has a choice of coming from a same direction or same side E is added as a syn addition, or it can add from an opposite side or anti-addition. Okay. So nucleophile now, nucleophile can be negatively charged, it could be negative, it could be lone pair. That's not something we need to worry about. Now what we have is a nucleophile is offered two facial attacks. So synfacial, antifacial. Facial means molecular face. Well, since we have two choices, offering those two choices is called stereochemistry. See, just the way regiochemistry is an offer of two choices. Regio means region. Within the molecule, that is one region, that is one region. So we ended up choosing the electrophile attacking this carbon as the region, regional selectivity. Stereo means facial. Facial, you know, stereo, dextro, levo, RS, right? We are talking about mirror images. So nucleophile can go from the top side or bottom side. Now having those two choices, this is a two choices offered of two choices. Offer of two choices, right? Now, do we have a reason to block? See, if this nucleophile encounters this E and doesn't want to, if it doesn't want to go there because it doesn't like going near it, so I'm going to write now, if E based on its nature. What nature does it matter? What are the natures? Size, electron richness, those are the two factors that come in play. If E is fat, then nucleophile says, now why should I go that way? I'll come this way. If the E is electron dense, that means there are a lot of electrons here. And what do we know? Electrons are also rich here. This has to be charged or rich in electrons. It's a nucleophile. So nucleophile will say that if there are electrons here, you know what, why do I get repulsion there? I'll go this way. So if E based on its nature, which are size or electron density, offers any objection or resistance, there will be a stereo choice. What would it choose? It would be prefer nucleophile, then prefers anti-facial attack. Nucleophile can prefer antifacial attack. Otherwise, 50-50. Means what? 50% of the time it can come this way, 50% of the time it come this way. What that means to us is natural statistical bias is not there, because if the nucleophile and E are not related to each other, they have no interest in each other, no hatred towards each other, 50% of the time it's going to come this way, 50% of the time it's coming this way. But if E has some stench that nucleophile doesn't like, if E is large, bulky, nucleophile says, why do I have to squeeze myself there? Then it says, I'll go this way. So if it does this way, I'm going to show you now how the picture is going to change. The picture is going to tilt now. The synfacial attack, synfacial attack and antifacial attack. By the way, I don't plan to place these notes on the web. May not be a bad idea for you to write these as I'm talking, because giving notes was not the goal here. Okay, you need to prepare your own notes. So let's say it attacked from the top. Now what will happen? It has to tilt now. So that carbon, let's say those two carbons, and E has finished its number, and this has done its job of tilting. So this part is not going to change, right? Now what's going to happen? If the nucleophile comes this way, to make space for it, these two have to go downward. So the R1 is going to tilt here. Goes R2. And then R1 is going to go there. See how they are not going to be planar anymore? They're going to tilt downward, and the nucleophile will go here. Right? So this is when nucleophile and E are on same face of the molecule. That's why it's synfacial. What would happen if antifacial? Antifacial means nucleophile comes from bottom side. Again, this part stays the same. E stays here, right? And that H stays here. Let's not rush anywhere. This is a slow process. Okay. Now what's going to happen? If the nucleophile comes this side, to make space so that nucleophile can sit here, this R2 has to flip, right? And R1 also has to flip, right? So the molecule now has both sp3 carbons. Okay. Now what did we decide? We realized that if E offers some type of resistance, this is more than 50. So I can write this is 50% or more. And when it is more when E says don't come here. Here this one is going to be 50%, that's the maximum, or less. Why less? If E says I don't want you here, then the nucleophile has to go that way. So the chances of this happening, when these two have to add up to 100%, is it possible? Is it possible? This is 100%. Yes, 0% possible. It is possible. Why is it possible? If this is so big and so rich in electrons that nucleophile says, I'm not going there, not even one chance, I'll go all the way here. Entire time it's going to come this way, 0 times is this way, just the way. This is 0%. This is 100%. That's a selection. Okay? Keep in mind, it can be 100%. This can be 0%. When this is 100%, this is 0%. But if this is 50, that means if E is tiny, it doesn't have electron problem, so it can simply say, alright, do whatever you want. In that case, it's 50%. That's why I said 50% or less, 50% or more. Okay? So it won't be, antifacial will never be less than 50%. Synfacial can never be more than 50%. That's another thing to be understood. Because there is no reason why nucleophile Why electrophile will call the nucleophile to come over here. Electrophile will never call this to come over here because there is no reason, right? No two atoms would like to huddle unless, I mean, they have a bulk problem already, right? So this is the story of electrophilic addition reaction, and addition because a pi bond is gone, replaced by two sigma bonds. And sp2 hybridization is gone. sp3 hybridization is created. Okay. Now let's look at these selectivities, regioselectivity and stereoselectivity. By the way, if we have a choice, this is stereoselectivity. So every one of the reactions that we are going to talk about, right now I have not identified who is my E and who is my NU. Okay? We have 20 some reactions that we need to talk about. That's why I want to lay a groundwork to show that this is not a single situation, single molecular situation. So keep in mind this idea of energy diagram. If you have, this is a regio choice. Now what will happen? What will happen, and I think I mentioned this last class before I left. What would happen if I have started with a symmetrically substituted alkene? If it was symmetrically substituted alkene, would there be a difference between C1 and C2? No, because formation of a carbocation here or carbocation here, both of them are going to be tertiary. Or if I have something like this, both of them are equivalent. Or if I have something like this, these are symmetrical. If they are symmetrically substituted, so let me write that down. If the alkene is symmetrically substituted, then what is going to happen? Then there is stereochemistry, there is a regiochemistry. There will be regiochemistry. Why will there be regiochemistry? Of course you will have two carbons to play with. Of course you have that carbon and that carbon, that carbon and that carbon, that carbon and that carbon. So the choice will be there. But what will happen? Since C1 and C2, as I have noted here, C1 and C2 are these two carbocations. In these three cases, C1 and C2 are going to be identical in energy. Both of them are either secondary, both of them are tertiary, or both of them are primary. In that case, there will be no regioselectivity. No regioselectivity means what? We are not picking one carbon over the other because both of them are going to be identical. Does it mean the reaction is not going to happen? Reaction is going to happen. In that case, your products are going to be 50-50. Here is one more thing to keep in mind. Before I proceed, I want you to keep one more thing in mind in these reactions, because since I'm talking about a stereo issue, let me expand on that stereo issue and look at the choices, okay? Look at all the choices that we will be encountering. I'm going to take a specific situation, specific scenario, and this will probably clear our doubts. And this is a lot of choices that we need to talk about. I am going to say, usually we write pH for benzene, like Me for methyl. So it's not a benzene, it's a phenyl, which is benzene ring. Okay, pH stands for phenyl, Me stands for methyl, Et stands for ethyl. I believe you have been notified about these what do you call notations. So let's say I am taking a situation. Let's take a very clear example, very elaborate example. Maybe I should use color for this one, and color will help a little bit. So let's see what will happen. So let's say I have an alkene, and I'm going to start with a three-dimensional picture now, and this is to be watched. Okay, and let's say this is my starter alkene. Okay, this is my starter alkene, and I'm going to write a pH, means benzene ring is here, and Me here, pH and Me here. This is a very complicated conversation, so pay attention. There is a pi bond here, you understand that, right? And let me write this to be, what should I write? I'll make a Me here, right, and H here, just for the sake of. That has nothing to do with, you know, any other situation. So I have an alkene. Okay, I have an alkene. Now I'm bringing a molecule which may not be easy to identify at this point. I'm going to say it is a ICl, and you may wonder, what is this ICl? This is iodine monochloride. It does exist, trust me. This is like I2 or Br2 or Cl2. Okay, now here is something that I'm invoking very carefully. There is a delta plus in this one, delta minus in this one, built in, which you would not find in Br2 or Cl2. Okay, so this is easier to handle. So when there is a communication between these two, but this molecule and this molecule are talking, now what might happen is you may have an interest shown that, by the way, this is the delta plus. It's not going to go to delta minus. Remember that. It's a electrophile that is going to be attracted. So let's say this is going to do this, right? There is a equal chance that this can do here as well. Remember that. There are two faces to the molecule. Just like a paper has two faces. That means the I can, first time it can come this way or this way. So that itself is one of the things that we didn't consider. We did not consider. So I'm going to consider that. So if that is the case, first of all, my first step itself is modified. My first step is what? Now, here we have to make a choice. I will have a, let me draw this. Oh, this is going to be very interesting. It's going to get big. So let's see that. This is pH. This is Me. There is a, I'm going to write a small drawing here. Okay. Me, H. So what happened in the first phase? Did I say H? I started talking. I started talking with these electrons, right? That's what it is, right? I started talking with these electrons. That means there is a transition state like this created. Is that correct? The transition state like this is created. Transition state means this carbon, this I are talking with each other. This is one of them. What's the other one? pH, Me. Lot of three-dimensional visualizations, okay? This is why you had a molecular modeling issue that you had to study and you were supposed to draw these pictures, chair and boat and all that. So now what is the other one? Now I might be talking like this. That means the transition state, a triangular transition state, is going to be like this. So those are the two choices that might happen. 50-50, by the way. Nobody is stopping them. It's a planar molecule. You can hold any page, Now, this will break into, you can see how complicated this can seem at this point. This has two choices. What are the two choices? The I will marry this carbon, or I will marry this carbon as this chlorine walks away. As this chlorine walks away, right? When they walk away, what's going to happen? This I has to marry this carbon or this carbon. In this case, I has to marry this carbon or this carbon. So those are the two choices. So those two choices we are going to draw now. Right? So let's say the I marries this carbon. In that case, your I will be linked here. Is that correct? But in the meantime, of course, your Me is going to go there, H is going to go there, and these are going to stay exactly where they are, because that's still sp2, pH, Me. Now you have a empty p orbital created. In this case, however, when I is connected to this carbon, because the I has a choice of coming here or here. So if the I is connected there, then what's going to happen? pH will be here, Me will be here, but that Me and that H are going to be in same place, and there will be the empty p orbital, right? In this case, what happens? Again, this one, remember there are two choices, okay? This one will have two choices again, that or that, okay? In one case, you will have I connected to this carbon. In the other case, I will be connected to this carbon, right? I'm going one step at a time, and let me finish the drawing then. So if I is connected here, the Me has to go there, and H has to go there, right? But this pH is going to stay here, Me is going to stay here. Don't try to jump. There is no reason to jump, okay? But in this case, pH is going to be flipping this way. Sorry, this is the Me, and pH could be, I can write it here also if I want to, depending on the angle at which I am looking at. But these are going to stay exactly where they are, Me and H, right? So we have four possibilities now. In this case, you have a choice to make. Which one of them are going to win? Well, again, these both of them are equal, so which of these are going to win? You can see this is a tertiary, this is a secondary. You see, secondary means there is a hydrogen. This is a hydrogen. This is the Me and pH. So this is definitely not going to be the answer. So here is the choice. So we crossed it out. We crossed it out. Okay, this is not going to happen. This is going to happen. In this case, who will have the positive charge? Positive charge will be here. That means that is not going to happen. That's going to happen. Positive charge will be here. So we made one choice in this case and one choice in this case. So we had done the regio selection, right? We did the regio selection. Next comes the stereo selection. Now who is left around? Cl minus is left around. Cl minus. Cl minus. Well, what do we know about iodine? Iodine is big. Iodine is large. Iodine has electron density. This iodine has electron density. So if the chlorine wants to come this way, to attack this carbon, to go to this carbon, chlorine is not going to go this way. It is going to prefer to go from the top. So it's going to be antifacial. Antifacial means the face, in this case, face is downward, so it's going to be antifacial. Here again, chloride, not chlorine, chloride will not go this way. It is going to go this way, right? It's going to go this way. So we have a choice. Here again, we have a stereo choice. So I'm going to write only choice C1. Only choice C1. That means I will have what's going to happen? I will have this pH is going to go here, and Me is going to go here, sorry. Right? And you have seen Me here and H here, right? Now what happened? Our I went here, first step, and Cl ended up here, right? Cl ended up here. This is the final answer for us, for this one. For this one, this is the final answer. What is this one? This one will have, this one is going to continue, and this is not going to continue any further, right? And then only top attack is going to happen, not bottom side. So again, I have one product, only one product. So what is this? So if the I has been already attached here, my Cl will be ending up here, up, right? It's the only way. There is no other way to look at it. Well, that gives us a, where did I put Me? Me is going to be here. H is going to be here. And what would happen? If Cl comes here, the pH has to come downward, because this is a three-dimensional and it's a sp3 carbon now, Me, right? So it's an interesting way to look at it. Now here is very interesting that you can see what is the relationship between these two. Who are they related? They are, you can see they are simply mirror images. These are enantiomers. They are enantiomers of each other. In one case, chlorine is up, but they didn't switch, did they? They did not flip. So pH Me, pH Me, MEH, MEH. So these are enantiomers. That's a small gift of having learned stereochemistry. Okay. Now this is far more complicated. It can become more complicated if I take slightly different example. But this example illustrates to you the importance of two phases available. I want to emphasize this is, we are not going to analyze this much every example, but we have to be aware that these are the possibilities. We have to be aware these are the possibilities. So whenever there is a pi bond, you don't just add something and walk away. So if you look at, if you memorize, right? If you memorize, and as probably in the book, if you say, if I added H, Br, you can simply say, oh, H adds here, Br adds here, and you walk away. In most cases, your answer will be considered reasonable, right? But you should know there is more drama there. You have to know there is more drama there in this reaction. So when needed, we will be analyzing this. Not in every situation. Not in every situation. When needed, we will definitely use this type of thought process. Keep in mind, regiochemistry, regioselectivity, stereochemistry, stereoselectivity. Now, if there is no regiochemistry, there is no regioselectivity. So regiochemistry is essential for regioselectivity. Stereochemistry is essential for stereoselectivity. That means if you don't have two choices, you can't pick one over the other. You need two choices to be able to make one choice. If the choices are not even there, then these reactions called, when there is no regiochemistry, such reactions are called regiospecific. Remember that. There are other reactions, there are some reactions we call them regiospecific. Similarly, when there is no stereochemistry, the product will be considered stereospecific. Or not, because some cases it's not stereospecific. This is another thing that we need to talk about at a later date, not now. But only when you have stereochemistry, that means choice of attacking from the top or bottom in a carbocation, then we make a selection. If we don't have a choice, there is no selection. You're going to take it as it comes, right? If there are choices, if there are two choices, then you are given an intelligence decision making process where you can say, okay, I will choose this one over this one. Okay, and this is the second complicated issue of alkenes. That I want you to be aware of this drama that is happening in alkene reactions. Now let's start taking what are our E and Nu. So let me list now E and Nu. For most part, first one we are going to use E as a H plus, Nu as a Br minus. In second case, E is H plus, Nu is a OH2. Remember, there is not such thing as a OH as a anion. We will use Br and Br minus. Okay, we use Br and H2O. These are all cases that we are going to look at. Then we will do OH and OH. We are going to use H and H. Which one? What else? Those are the PROH halogens. Okay. And then sometimes we use just the O as an insert. Just the oxygen attaches both. It becomes electrophile and nucleophile. CH2 or CCl2. Those are both functioning as electrophile as a nucleophile. So these are our initial attack. These are the examples of our initial reactions. Okay. So the reaction of this reaction is called hydrobromination. Hydrobromination. If adding H and a OH, so what would happen? What would happen if I use hydrobromination? So let's start with hydrobromination in non-aqueous solvent or non-polar solvent. That's very important. Solvent has an issue. I think I told you the role of a solvent is just to facilitate reactants coming in contact with each other, right? Reactants colliding with each other. And what should not solvent do? An ideal solvent does not participate in the reaction. Unfortunately, water is not an ideal solvent, right? So we pick CCl4. CCl4 is a common solvent used as a solvent, that non-polar solvent By the way, since these reactions involve charged bodies are involved, right? Charged bodies are favored in what solvent? Charged bodies are favored in not polar solvents. Remember that, right? Charged bodies are ions are favored in polar solvents. Completely non-polar, I think sodium chloride, for example, doesn't dissolve in gasoline, but it does dissolve in water. So H2O is a polar solvent, and we can use alcohol, CH3OH. Any alcohol can also be a polar solvent. So those are the solvent issues. Solvents sometimes cause a lot of interesting diversions in the reaction, and that's one of the problems we are going to face in some of these reactions. Okay, first study hydrobromination in a non-aqueous solvent. So I'm going to take any example. It doesn't matter whether whatever contraption I have, whether I have that or simply that, the idea is still the same. The reaction is still the same. It's an unsymmetric alkene, so there is a regioselection. So if I treat it with HBr, now when I use HBr, I could have done this with HI, HCl. So this is called hydrohalogenation, right? Hydrohalogenation. I could replace that HBr with HCl and HI. Keep that in mind. Don't have to take every example. And CCl4 should give you the message that we are not going to do this in aqueous solvent, and that means there are certain things are forbidden to do, and we'll talk about what are those things that we can't do. So the product in this case turns out to be exclusively that. Okay, that is the product. So this is how we write. Whenever we write mechanism, whenever we try to write mechanism, we first write reaction, reactant, reagent, solvent, arrow, reaction. That's it. Now, if there is anything byproduct, if there is something else produced along with it, we call it byproduct, because this is an organic compound. We focus our attention on organic compound. So let's look at the mechanism. Mechanism. HBr. Now keep one thing in mind about HBr. Let's talk about how to call this molecule. HBr is hydrogen bromide. It's hydrogen bromide. Does it dissociate in CCl4? Answer is no. Because it's a non-polar solvent, it won't. Answer is no. But HBr in water is not called hydrogen bromide. What is it called? It is hydrobromic acid. Look at the name difference. That's hydrogen bromide. It's a non-aqueous solvent, hydrogen bromide. In an aqueous solvent, it is a hydrobromic acid. That means what? And it's a strong acid. pKa somewhere around 8, negative 8. That means it doesn't exist like this. It becomes H3O plus AQ plus Br minus AQ. That's what it exists as. Even before it start talking with this, if you do this reaction in water, this is what is going to happen. Keep that in mind. Okay. So this is true about water as a solvent. When an acidic molecule is placed in water, it dissociates. There will be dissociation. Keep that in mind. Especially when it's strong acid, these ions are no longer associated with the H. But in this case, that bond is very strong, HBr. That's a single bond, HBr bond. Okay? We have to be mindful about a sigma bond here, H and Br. In this case, there is no bond there anymore because it got dissociated. So, that's the reason I have to say that is because you might mistake that HBr for HBr in water. That HBr and that HBr are different. That HBr is in CCl4, it is married with H, and Br is not willing to let go of that H. It's not happy. However, there is a delta plus, delta minus is there. That's born with the problem. That we can't do anything. So now what happens in case of reaction? Reaction is this. Now CCl4 is just there. It's just a part. It's a solvent. It is not participating. So we don't really have to, as long as I identify that, I don't really have to rewrite it during the mechanism. Because there is a delta plus, delta minus, and that bond has to go that way, right? That has to happen. Now, all that together in a transition state can be shown this way. Now, watch as I am writing, because you should not leave out anything. If I expect you to draw, you should not leave out anything. And there is a dagger on the top of it. That's the transition state. Transition state should have a dagger on top of it. Two lines with a cross. Okay, not a simple cross. It's a double line and a cross. Okay. Now this we know, since there is a regiochemistry, it has two choices. It has two choices. What is the choice? H can either marry to this carbon or H can marry to this carbon. So you have a choice of, now I'm going to do a, let's see if I can do a three-dimensional. No, let's not. I started it anyway, so let me. Okay. Remember, there was one H and then the new H. This is that new H. There was one H already. See, there was one H already there. That H is there. Okay. A new H came in. Positive charge will be here. That should be methyl, right? Because that's a methyl. Okay. There is a hydrogen. So this is the new H that came in. Would it make a difference which one is which? No, it doesn't make any difference. However, what was the other choice? Other choice was this. Where I have a H added here, right? Me went downward, right? And then p orbital is right here, and then H is still there. Okay. Now this is a secondary carbocation. This is a tertiary carbocation. And we made a choice that we are going to make a choice. This is not going to happen. That is called regio selection. Showing these two choices is regiochemistry. Showing them as this is a choice, this is a choice, but then crossing one of them is saying that I'm not going to use this, I'm going to proceed with this one only. And what is it based on? Carbocation stability. Alright, now comes our next step is this bromide which was kicked out. There is a bromide in the non. Is bromide happy in CCl4? Is bromide happy in CCl4? Bromide is very unhappy in CCl4. It's a polar ionic molecule. It's a non-polar solvent. It doesn't want to stay this way. Does this positive charge stay happy in this solvent? No. There is a misery in positive charge. There is a misery in negative charge. They quickly get married with each other. Now comes the issue. How do they get married? Can Br go this way, or should it go this way? Where should it go? Top of the plane or bottom of the plane? In this case, who is the one that could offer any resistance? The one that is offering is the hydrogen. Is hydrogen big enough to offer any resistance? No. So H has no bulk. That's one of them. H has no electron density. That's number 2. If there is no bulk, no electron density, then Br can choose 50% of the time this way, 50% of the time this way. Is that correct? 50. Because it doesn't have to pick a side now. Both sides are just as good. So now you have a 50-50 chance of having this product. So the product now is going to be, and we chose to add bromine here, sorry, H here. We chose that. Then Br can be synfacial. That's a synfacial. Or antifacial. What does antifacial means? Opposite side. So how will it be in opposite side? Of course, this is going to stay where it is, but bromine now has been added from the opposite side, right? So the Me now flipped upward, this Me was flipped downward. So essentially Br and H are opposite this side in this case and same side. Now would it really make a difference in this case? No, in this particular case it makes no difference because the second hydrogen is not going to make it any chirality. It's not going to make any chiral. However, when you look at this particular location, right? This particular location, if it is chiral, is it chiral? I'm just going to write if it is chiral. If it is chiral, that's very important, if part. If it is chiral, you will have 50% R, 50% S. What does that mean? Racemic mixture. Then you will get a racemic mixture. Why would you get a racemic mixture? Well, 50% is D, 50% is L. It has to be racemic then. Is that correct? Right? Is this chiral? Let's redraw the structure. Is this molecule chiral? That's the end goal, because we don't care for those hydrogens because that's not a chiral center. That's not a chiral center because it has 2 chiral. Is this a chiral molecule? This is non-chiral. Why not chiral? Because you can see that while this and this one, this and this are different, this one, this side and this side are same. So this is a non-chiral or achiral molecule. Okay. This happened to be ring. Does it have to be ring? No, it didn't have to be ring. That means, is it possible that I might get chiral? Yes, I can easily get a molecule which is chiral. In that case, I'll have a 50-50. Otherwise, both of them are equivalent. Okay. So let me take one more example of this one and move on. So what would happen if I take a let's take that. I have to make that. Okay, sorry. Okay, let me take this example with HBr. I have a reason to draw this with HBr, or I can do this that'll work, plus HI. Okay, I'll make it HCl because I used HBr earlier. Just want you to be aware. Now if you use CCl4, we have to look at the final answer now. rather than going through individual steps, go straight to final answer. Final answer is you are going to have H add here, Cl add here. H add here, Cl add here. Keep that in mind. Why? Because if I added H here, there will be primary carbocation. If I added H here, primary carbocation. That's a step number 1. Right? Step number 1 is adding H. So you got to look at where is it first adding. First adding is H. That's going to get complicated when I have other molecules come along. So this has to be clear. So what's going to happen is you will get a that or that. This is Cl. Those are the two choices you are going to get. In this case, those two choices are you going to get. I hope you are, catching up. Since those two are the choices, we can definitely see a chiral center here, because this is the ethyl group, this is the ethyl group, this is a propyl group, methyl group. So this is a chiral center, that's a chiral center. You are going to get enantiomers. This is if this is dextro, this is levo. So these are enantiomeric pair. And since the hydrogen that was added in step number 1 doesn't offer any resistance, these are 50-50, that means this is going to be a racemic mixture. So you are going to have a racemization 100%. Here also same thing. There's a ethyl, methyl and hydrogen that was not shown, right? Doesn't need to be shown. There's a hydrogen. Okay? So this is again a 100% racemic mixture. But that has nothing to do with actual reaction. Keep that in mind. That has nothing to do with the overall reaction. Reaction is going to happen. But that's a new characteristic. We can talk about extra knowledge, extra information about this molecule. Keep one more thing in mind. If I start with that molecule, this is not something currently applicable. Suppose I have this molecule. I'm gonna add one more group there. Yeah. So what might happen in this case is if I added HBr in CCl4. Now keep in mind this is a symmetrically substituted. That means I'll have a 50% chance of doing this, right? And I have a 50% chance of doing this. It's a 50-50 chance. That's a no selection. There is no regio selection here because carbocation is not going to be differentiated. On top of that, we have a stereo, also no selection. So we will have these two pairs and these two pairs. Now if you look at it, only this molecule is chiral, this is not chiral. This part is non-chiral pair. But this is the chiral pair. So what is the message here? If you do HBr reaction to a symmetrical alkene, or symmetrically substituted alkene, there is a likelihood that you might get multiple products, And one thing in organic chemistry is if you get a multi-product, it's not really something positive sentiment. People will say you're not being selective. So if you get a mixture like this, separation is going to be a problem, right? If this is a reaction that is used for producing something valuable like drug, medicine, this is one of the worst way of doing it, because if you get a mixture, you're not going to be able to separate them, you're not going to be able to use them for any purpose. This is wasted effort. So many times when you do organic reactions, we want to create a way where only one of the product is major, rest of them are something that can be washed away. That's the message has to be taken. So having racemic mixture is not a good thing. Having multiple product is not a good thing. Having only single product, one single product is what we need to go by. And that's the ultimate goal of organic chemistry. Just producing a mess in a reaction mixture is not really a good way of showing that I learned organic chemistry. Okay, this is where I would like to stop.